I start talking about organic compounds, this is going to be less quantitative and way more qualitative. A lot of formulas, structures, and so on. And the first conversation that we're going to have is about hydrocarbons. I think you can read the story about firefighters on your own. But the very first part of today's lecture, we're going to just define what is the difference between organic versus inorganic compounds. Basically, the fundamental idea of what organic compounds are is that they must contain carbon and hydrogen. Okay? For example, this methane, organic compound. Carbon dioxide, inorganic compound. Now, for the full disclosure, when we say that an organic compound is made from carbon and hydrogen atoms, we can say that this is the bare minimum. What do I mean by that? Here's the formula of glucose. Okay? Does it contain carbons? It does. Does it contain hydrogens? It does. But it also contains oxygen. So when I say bare minimum, I mean that carbons and hydrogens must be present. Okay? They can contain oxygen, sulfur, nitrogen, phosphorus, halogens, even metals. And you are, as a matter of fact, surrounded by various organic compounds in this particular room. The material that this table is made of, the desk itself is organic. Your t-shirts are organic. Okay? When we write the formulas for organic compounds, the carbon goes first, then hydrogen, then everything else. You can see in my example of glucose, I wrote carbon first, then hydrogen, then oxygen, and whatever is left. So, all organic compounds have covalent bonds that connect carbon, hydrogen, and all other elements to each other. They practically always have relatively low melting and boiling points. It's not always true, as I mentioned, the desks that you are working on right now are organic. You know, they're not melting in the room, and they won't melt if you put them outside, but they're fairly easy to melt even if you get probably a lighter. The heat will be enough to start melting them. Many of them are flammable and can undergo combustion, essentially burning. And for the most part, not all, but many more organic compounds are insoluble in water than organic compounds that are soluble in water. Okay? Now, if you will start comparing organic and inorganic compounds, you may notice that inorganic compounds often have high melting and boiling points. For example, sodium chloride. On the other hand, organic compounds, such as propane, is a gas at the room temperature, so it has very low boiling point and even lower melting point. So this table provides you the comparison between organic and inorganic compounds. So first of all, the elements that are present. I want to emphasize once again that organic compounds must contain carbon and hydrogen as well as other elements. Inorganic compounds can contain virtually anything, for example, metals, nonmetals such as sodium chloride. The particles that form organic compounds are molecules. For instance, the molecule of propane, which consists of 3 carbons and 8 hydrogens. For inorganic compounds, it can be ions or, not necessarily, nonmetals. Okay? I would add here when you start thinking about this, for example, phosphorus pentachloride is inorganic, but it does not contain any metals. Okay. Bonding almost exclusively covalent for organic compounds, and for many inorganic compounds. What's going on with my screen? Hold on a second. For many inorganic compounds, bonds can be ionic. Just a second. Okay. So, as we mentioned before, for the most part, bonds within organic compounds are covalent nonpolar. It's not always true. Obviously, electronegativity will describe what type of bond particular atoms will form, but, for instance, bonds between carbon and hydrogen are nonpolar. On the other hand, within inorganic compounds, many bonds are ionic, and very few are nonpolar covalent. Okay. Melting points, we mentioned that, usually low for organic compounds and usually high for inorganic. Organic compounds, most of them are flammable, well, inorganic or not, and organic compounds are not soluble in water unless there are some circumstances when they are. Most inorganic compounds are actually soluble. Any questions so far? All good? Okay. So let's talk about what hydrocarbons are. So hydrocarbons, as you can guess from the name, contain exclusively carbon and hydrogen. Okay? An important rule that you must remember in all organic compounds: carbon always forms 4 bonds. For example, in this molecule of methane, you can see that carbon forms 1, 2, 3, 4 bonds. In this molecule of ethane, each carbon forms, so left one forms 1, 2, 3, and 4. And the right carbon forms 1, 2, 3, and 4. Sounds good? If all bonds that carbons form either with each other or other molecules are single bonds, we call such hydrocarbons traded. Any questions yet?
So, are those bonds related to the electrons in the valence shell?
Absolutely, yes. The bonds are formed by the electrons in the valence shell, and it's actually a very good question. So you can represent this molecule the following way. First of all, let's take a look at the periodic table. Carbon is located in group 14, which means how many electrons does it have on the outer shell? 4. I'm going to do it on the side here. So 2 carbons, each has 4 electrons, right? Make sense? We also have hydrogens. How many electrons does a hydrogen atom have on the outer shell? 1. So we have 2 carbons, right? And they're going to use 2 electrons to form a bond between themselves. Good? Following, everybody? Right? Now, what about hydrogens? So, hydrogens don't need 8 electrons on the outer shell, they need just 2, because they are in the first period. This is so annoying. So if hydrogen that forms bond here, 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 it's acting up. I know it happens sometimes. Okay, so I think we finally got this. Does that make sense, everybody? Okay. Give it a second to process things in their lives. Normal. That's expected. I knew what I was doing. Don't get me wrong. Okay. So the first molecule that we're going to talk about is methane. Okay. So if you look at the orientation of the bonds here, I want to focus your attention on this part of the molecule. The bonds are oriented so that carbon is located within the figure that we call tetrahedron. So imagine this. You have a triangle as a base, and there are 3, it's not side, edges, that stick out of that triangle. So in this tetrahedral orientation, hydrogens are located within the angles of the triangle, tetrahedron, okay? And the carbon is in the center. The reason why these bonds are oriented this way is the repulsion between the electrons that form those bonds. We talked about it very briefly, remember? That the bonds have to be positioned in a way that the electrons are as far as they can from each other. And this is why this 109 degrees angle here is the optimal angle for the bonds to exist. Am I making sense? So there are several ways to represent an organic compound using formulas. The A is the space filling model, which does not have bonds. Basically, atoms are directly connected to each other. It looks very cool, but it's really hard to work with on paper. B is called ball and stick model. We're going to play with ball and stick models in the lab at some point. Okay. In this case, you can see bonds and atoms. Traditionally, in organic compounds and the models of organic compounds, carbons are black, hydrogens are white. Okay, so carbons are black, hydrogens are white, oxygens will be red, and then colors for nitrogen and sulfur and phosphorus can be fairly different from model to model. Okay, now this is wedge dash model, and I'm going to talk about it for a second because it's really important for you to understand why different bonds are represented with the different graphics. I'm going to ask you a series of questions, all right? Good? So there is a plane of the page that you're looking at. The plane of the screen, okay? Make sense? So the idea is this. These bonds, the ones that are represented by simply lines, are in the screen plane. Does that make sense? They are on the screen. This bond, the dashed one, shows you that the hydrogen is behind the screen. And the wedge shows you, the dark black wedge shows you that this hydrogen is in front of the screen. We aren't going to use this representation often. It shows you the structural features like 3D structure. It allows you to represent 3D structure of the molecule. We're not going to use it often. We're going to mostly using expanded and condensed structural formulas. So in expanded structural formulas, we draw all the bonds. In condensed structural formulas, we always omit the bonds between carbon and hydrogen. Does that make sense? Meaning that we know there are 4 bonds, we just don't draw them. Any questions on the representation? So now let's take a look at the next saturated hydrocarbon, which is ethane. Okay? So this is space filling. This is ball and stick. Now, when you start looking at the wedge dash model, you can see that this hydrogen, and these 2 carbons are within the plane of the screen. Am I making sense at this moment? Good? These 2 hydrogens are in front of the screen, while these 2 hydrogens are behind. And you can see that in this molecule as well, carbons form that tetrahedral orientation of the bonds. Am I making sense right now? So this is going to be expanded structural formula. You can see all the bonds between all the atoms. And this is going to be condensed structural formula. You see that? We only show the bonds between carbon atoms, not hydrogen atoms and carbons. You know, we condense them. Any questions?
Yes.
Go ahead.
They have differentiation
Say it again?
Why they had different shape? The shape? The shape.
Are you talking shape?
Yeah, the structure.
Which structures are you talking about?
General, everything.
Well, because they different representation. They represent the same molecule, just do it different way. So this is space filling, which does not have any bonds between atoms. Atoms are attached pretty much to each other. This is ball and stick, same idea, but now we expand the bonds. This is the wedge dash model, which shows you the relative position of hydrogens, whether they are closer to you or farther from you. And these structural formulas, they don't really show you the position of hydrogens, but they show you which bonds are formed. So, as a matter of fact, two last ones, the expanded and the condensed structural formulas, you can't really fully appreciate the shape of the molecule. Does that make sense? So they're not really reflecting the shape of the molecule per se. And here's the thing. So this is the butane molecule, right? Butane has 4 carbons. Each carbon is connected to either another carbon or hydrogen, you know. Each carbon forms 4 bonds. And what you see here is essentially expanded structural formula. Okay? Make sense? Now, the question is to predict the shape around each carbon atom. Here's the rule. If carbons form only single covalent bonds, and all bonds in this molecule are single bonds, carbons will always have tetrahedral shape in organic compounds. We can pretty much write this. Saturated hydrocarbons equal to the statement only single bonds tetrahedral shape. Okay? Question so far? So right now, we covered 3 different hydrocarbons. Methane, ethane, and butane. All 3 of them, belong to the group called alkanes. Okay? Alkanes are characteristic the main characteristic is that they only have single bonds between carbons. Does that make sense? This is the rule. Alkane always has single carbon-carbon bonds. So this is what I just told you. Alkanes contain only single bonds between either 2 carbons or a carbon and a hydrogen. And they usually form a chain of carbon atoms, although it's, well, alkanes, yes, always a chain. Chain can be branching, as we will see, but it's always going to be a chain. There is a so-called International Unit of Pure and Applied Chemistry, basically a bunch of nerds, chemistry nerds, that get together and create the rules, and then the rest of the humanity suffering under the boot of those rules. But without those rules, we would be ungoverned. Essentially, they created a system how to name an organic compound, so you can figure out the structure based on the name, and you can write a name based on the structure. Clear? All alkanes have a name that ends with A-N-E, and Greek numerical prefixes are used to name alkanes with more than 4 carbon atoms. So, here's what I'm going to do. I want you to, right now, ignore line angle formula. We're going to go back to this later, okay? And I want you to focus on the name and the formula. So, if there is one carbon atom, methane, 2 carbon atoms, ethane, 3 propane, 4 butane. Now we start using Greek prefixes. Okay? 5, pentane, like pentagram. 6, hexane, hexagonal, okay? 7, heptane. 8, octane, okay, like octave in music. 9, nonane. And 10, decane, like in decathlon. Okay, does that make sense? Any questions on this? Does it make sense, folks? Because now we're going to demonstrate the mistake in this table. What is a line angle formula? I'm going to do it on the side. Let's say I want to represent a compound called propane. You follow? Okay? How many carbons are in propane? 3. 3 carbons, right? So what we can do, we can say that this is going to be our first carbon, this is going to be our second carbon, and this is going to be our third carbon. So, as you can see, well, nobody puts the dots, so line angle formula for propane, you can draw it this way, you can draw it this way. Every angle or end represents a carbon atom. You can ask, wait a minute, what about hydrogens? Well, I'm going to ask you a series of questions if you don't mind, okay? So this carbon in the center, how many bonds does it form with 2 other carbons? How many bonds does it form with 2 other carbons? 2, right? 1 and 2. Make sense? How many total bonds can the carbon atom form in some kind of organic compound? It's the rule, huh? 4. and form 4 bonds. So this central carbon already used 2. How many bonds does it have left? So it will form those 2 bonds with 2 hydrogens. Does that make sense to everybody? This carbon, at the end, how many carbon-carbon bonds does it form? How many carbon-carbon bonds? How many bonds this carbon forms with other carbons? 1. Look at this. Here's what I'm going to do. Essentially, this is what we have. See that? So there's 1 bond that this terminal carbon forms with another carbon. Total is 4. How many bonds does it have left? 3, right? It used 1 bond to connect to a carbon. It can use 3 bonds to connect to 3 other hydrogens. Does that make sense to you? Now, I want you to take a look at this table and tell me if you can spot a mistake. All 10 of them, actually. There are 10 mistakes in this table. Say again? Exactly. So line-angle formulas are misaligned. Am I making sense? We just talked about a propane. It should go here. Ethane should go here, right? Does that make sense? Butane should go here. Does that make sense to you? So they just misalign pretty much. So we're going to use a lot of condensed structural formulas because, to be honest, the bonds between carbon and hydrogen are kind of boring. Okay? There is none. That's a great question. You're talking about the line-angle structure? There is no line-angle structure for methane. You can't draw a line that consists of a single dot. It's not a line. Am I making sense? So we just don't use it for methane. And methane is the simplest organic compound. Seriously. And it's just, we don't have any other than condensed structural formula. Okay? So, here's the deal. When you look at this atom or group, you can say, okay, this carbon forms 2 bonds with other carbons, and it also forms 2 bonds with 2 hydrogens, but you just don't write it down. Does that make sense, folks? Everyone? Right? Good? So, basically, when you see something like that in the condensed structural formula, this is what it means in the expanded. When you see CH2, this is what it means in the expanded. Any questions on this representation here? You've already seen, I'm not going to spend too much time on that. You've already seen that alkanes can be represented as a ball and stick. Okay? You've seen expanded, condensed, line angle. What is the molecular formula? Let's go back to propane. The structural formula for propane is this. How many carbons do you see? 3. How many hydrogens do you see? That's molecular formula. And there is a fairly simple rule how to write down a molecular formula for any alkane. Any question? No? Good. Okay. So, here's the thing. General molecular formula for alkanes. So what does that mean? If you have n carbon atoms, put whatever number you want instead of n. They will form bonds with 2n plus 2 hydrogen atoms. Does that make sense to you? Let me give an example. C10. So n equals 10. What is 2n then? If n is 10, 2n is 20 plus 2. Okay. Let's say n is 12. How many hydrogens? 26. 2n plus 2. You don't need to memorize anything beyond 10, believe me. Okay? Questions on this part?
So,
yes?
If the molecular formula like the C3H8, what is the condensed structure?
Okay, this is, okay. This is the condensed structural formula. Okay? Now, this is, to your question, this is the expanded structural formula for butane. Now, all these formulas are appropriate formulas for condensed structure. Question may arise, why would we use anything beyond that? In some situations, when you have a reaction and you want to sort of emphasize a position of an atom, you may want to change the orientation of carbons just to illustrate where, I don't know, hydrogen attaches or where hydrogen is taken away from, stuff like that. Make sense? Conceptually, there's no difference. It's the same compound. And these are line angle formulas, so you can see there's 1, 2, 3, 4 carbons. And we don't write hydrogens. Does that make sense? Any questions? Right, so cycloalkanes. Well, cyclic. Now, why do we call them alkanes? Because all bonds are still single bonds. They are, in other words, saturated. Okay? Now, because of that cyclic structure, cycloalkane will always have 2 fewer hydrogen atoms compared to the open form with the same number of carbons. Here's the thing. Look at the propane. The formula, molecular formula is C3H8. in cyclopropane, the formula is C3H6. So we can say that the general formula is CnH2n. Good? Everybody? Making sense? Let me know if I'm going too fast and you want me to like slow down or, keep the screen open for you. All good? Moving on? All right. So these are some common cycloalkanes. These are line formulas, these are condensed structural formulas, and these are ball and stick models. The names are derived in the same way, so if you have a linear alkane that is called propane, its cyclic version will be cyclopropane. A linear 4-carbon butane becomes cyclobutane. A linear 5-carbon pentane becomes cyclopentane. Am I clear? I like to kind of give you sort of some facts, maybe. It's been established that the most stable cyclic structure is the one that has 5 to 7 carbons. Or whatever atoms. Make sense? So, these two guys, fairly stable. These two aren't. Interesting story about cyclopropane. It was used as an anesthetic before nitrous oxide with the laughing gas. And the only reason why cyclopropane usage was stopped, imagine that you are doing a surgery, but your patient is put to sleep by an extremely flammable gas. Like seriously, any spark, and it can cause an explosion. It was just unsafe from the, the fire safety standpoint. It worked fine. It was like no side effects. It was good. Just fire safety. Now, you can substitute a hydrogen with another atom or a group. Okay? So, you can have a side group that contains a carbon. You can consider it a branch. Or often it is called substituent. So we're going to learn how to write the names of alkanes with certain substituents. I don't remember. We didn't talk about it. So now it's time to talk about the very important concept in organic chemistry. Isomers. So what is an isomer? Isomers have same molecular formula, but atoms are arranged differently. So effectively, the number of each kind of atom is the same, but they are connected to each other by bonds in a different order. So, here's the thing. If you take a look at butane, right? How many carbons, which are represented by black balls, how many carbons do you see? 4. And the white balls, which represent hydrogens, how many of them do you see? 10. Now, when you look at the bottom molecule, how many carbons do you see? How many hydrogens? But those are not the same molecules. Do you agree with me? They're different. They're structurally different. Now, isobutane, iso from isomer, is the common name. Okay? Does that make sense? Common name means that that's what we use in our day-to-day life. Okay? It's not IUPAC. So, let's exercise this. So we're going to draw 3 isomers of pentane. I'm going to draw it in a way of a condensed structural formula. Okay? This is your pentane. Any questions on this? Good? Now, what else can we do? What do you think? Well, we can take one group, like one carbon, and move it sideways. So, for instance, this. That make sense? How many carbons do we have in this formula? How many hydrogens? All good. Right? So another option what is the third isomer? Okay, let me see. What if, well, let's see if we can get, because I can see, let's do this. Oh, yeah, I'm an idiot. Okay, there's another option. So you do this. I'm going to make it closer to the left. Okay, makes sense? If you count carbons, there are 5 of them. If you count hydrogens, there are 12 of them. All right, we good? Clear? Everyone? Now, I'm going to throw a curveball at you. Let me draw another formula. The red and the blue molecules, are they the same or are they different? This one and this one. Bingo, they are the same. Because you can flip them. Like carbons and hydrogens do not have, they're not individuals, you know, they're the same. So, same formulas. Sounds good? Okay, so this brings us to the whole concept of substituents. So substituents are individual atoms or maybe groups that are attached to the carbon chain. Now, here they say alkyl and halo groups. I'll explain what it means, why we call them substituents and not anything else, and why they're limited. So alkyl groups are basically groups of carbon atoms. For example, CH3, CH3, CH2. Okay, those are methyl and ethyl groups. Remember how we name them? You know, meth, eth, prop, like propyl, butyl. They have the YL ending. Now, halogen atoms can also be attached to a carbon chain. And if you have something like this, okay, chloro. If you have something like this, bromo. Does that make sense? All good? Fluoro, chloro, bromo, or iodo. Okay? Question so far. Now, you can see that there are some names that are not super conventional. For instance, isopropyl and isobutyl. Usually we don't, if we try to name substituents using IUPAC nomenclature, we often try to use sort of different approach to this. So, how do you give the name to this compound according to IUPAC? The first thing that you have to do, you have to identify the longest chain. How many carbons does the longest chain within that molecule contains? So the name for the alkane with 5 carbons, can anyone remember? Pentane. Okay? Now, everybody can see substituents here, right? What is the name of this substituent? How would we call it? The previous one. It's a chlorine atom, so it will be chloro, right? This CH3 group would be methyl. Is that clear? They are at the different carbon atoms, so you have to figure out the position. Am I making sense? Good? So here's the critical question. From which end of the molecule you start counting carbons? So should you go 1, 2, 3, 4, 5? Or should you go 1, 2, 3, 4, 5? Technically speaking, there's no difference. But IUPAC established the rule that the total sum of all the numbers must be minimal. So you can name it 4 chloro, 3 methyl, 4 plus 3 gives you 7. Does that make sense? Or you can name it 2 chloro, 3 methyl, and 2 plus 3 will give you 5. Does that make sense to everybody? Listen up. If it doesn't, it's normal. Don't think of it as a fundamental law of nature. It is the way we all agreed on numbering. It's like on the street that drove me completely bananas when we came to the United States, that you can have like 33,091 as a number of a house until I learned that it's actually like blocks and the actual number is last 2 digits and different, you know. But there is an agreement of how we use numbers. Same story. It's just an agreement. So the final name will be this. The substituents go in the alphabetical order. So methyl will be 3, and chloro would be 2. Okay? 2 chloro, 3 methyl pentane. Does that make sense to everybody? Okay, I'm going to rephrase it. Do you get a gist of the rules? Okay, now, here's the thing. When you have to name a cycloalkane, like if you, forget about this group for now, all 6 carbons in cyclohexane are identical. Does that make sense? They're the same. So it doesn't matter. You don't give a number. If you have just one substituent, you don't need to give a number. Okay? We good? Now, what if you are facing the opposite situation? You have a name and you need to draw a formula. So for instance, this example, 1-chloro-1,2-dimethylheptane. You start reading the name from the very end. And the first thing that you identify is how many carbons are in the longest chain. Heptane, 7 carbons. Then you start reading substituents. So it says 1-chloro. Conventionally, when you have a name, we usually do from left to right. Not mandatory, but usually that's what we do. So 1 chlorine atom here. Okay, we got this. Then we have 1,2-dimethyl. Di means 2. So on 1 and on 2, we have 2 methyl groups. Okay, does that make sense? Now, the very first carbon that is connected to both chlorine and alkyl, the methyl group, how many bonds does it form at this particular point? How many bonds? This carbon, the very first one, how many bonds does it form? 3. How many does it have left? Okay. Second carbon, how many bonds does it form right now? 3. Bond, bond, bond. That makes sense? So it has 1 left, hydrogen, right? All of these guys going to have 2 hydrogens at them, and this fella, 3 hydrogens. What type of structural formula is that? I'm checking whether you heard me. When all the bonds are shown, the opposite, expanded. When all the bonds are shown, it's an expanded structural formula. Okay, sounds good? See him?
The compound formula, you write it.
The condensed?
Not the compound formula.
Oh, you mean like molecular formula? Well, let's do it together, shall we? How many carbons? Really? 9. How many hydrogens? I need to count it myself. Ah, what? 13? I beg to differ.
I think Cosmo is 10. It's 15.
Let's just do like increment of 1 until we hit the right number. 19. So you have kind of 10 here, right, on both sides. 11, 12, 13. And then you have 6 more carbons and 2 methyl groups. And do we have anything beyond carbons and hydrogens? Chlorine. That's it. C9, H19, Cl. That's going to be molecular formula. Did I answer your question? Excellent. So now we're going to draw condensed structural and line angle formula. Let me see. Yeah, I think what we're going to do, yeah, we're just going to do this because I don't want to start properties. I'm just going to do the learning check and I'm going to kick you out. Okay, sounds good? And we're going to finish this after the experiment class on Monday. Okay, so what we need to do is to write down the formula for 3-bromo-1-chlorobutane. So first, longest chain. Which word tells you about the longest chain? Butane. So how many carbons? 4. Good? Then we start numbering. 1, 2, 3, 4. Right? So chloro, and you can see that in this case, bromo goes first because it's first alphabetically. Not because of the number, first alphabetically. Make sense? So chloro at the first carbon atom, and then bromine atom is going to be at the third. Good?
Is that what the numbers identify?
Absolutely. These numbers identify the position. Sounds good? So you've got this. The first carbon, how many bonds does it have left? Second carbon, how many bonds does it have left? I'm going to slightly redraw it. The third carbon, how many bonds does it have left? And the third one? Does that make sense? Okay, good? Cool? All right.